say a few words about how I got into studying ice, because I think you guys will find this pretty funny. I was an undergraduate at Caltech in Pasadena, and my first research project was to study the process of basically mantle convection inside icy satellites with my advisor, Dave Stevenson. And I was very frustrated because there was this free parameter that I didn't know anything about called the melting point viscosity of ice. And it seemed to be unconstrained to within a factor of 100. And depending on what value you plugged into the model, you could get these icy moons to behave in a lot of different ways. I found that to be very frustrating. So I went back to my advisor and asked him, well, what is going on with this melting point viscosity? And he laughed at me and he threw a copy of the Hobbs ice physics book in my lap. And he said, well, enjoy yourself, because you're going to spend the rest of your career learning about the viscosity of ice, which that has turned out to be the case.
I think you should tell everyone that book has 754 pages.
Yeah, it's great. I wanted to buy a copy, and they're very hard to find, so I waited, I think, for someone to die in England, and then I got a copy, but it cost me $800, so now I can throw it in my students' laps and laugh at them too. Okay, so since I'm very tired and I'm likely to ramble, and I know there are people here that just flew in too, I'll tell you the point of this talk at the beginning. I just want to get 3 points across to everybody. The first is that the solar system has thousands of objects that are planet-sized that are composed of water ice. These objects are a little bit different from the Earth. Instead of having just a very thin veneer of water on the surfaces of these sort of planets, tiny planets, the entire outer 100 or 1,000 kilometers of these objects is composed of water ice. So these are planets where water ice is really the bedrock of the planet. The second point is that most of these objects turn out to have liquid water oceans underneath about a few tens of kilometers of solid ice that's at a very low temperature. And then the third point, I want to set up what I'll talk about later in the week in my technical talk, which is that the process of tidal flexing, where these moons are actually deformed due to the tidal potential of the gravitational, it's the gravitational field of their parent planet, actually deforms these objects in a cyclical manner. So as they orbit around, they get stretched and squeezed every day. I want to talk about how I think that this is the most important factor for driving resurfacing on icy satellites. Okay, so we'll look at the first point. Here is a sort of inventory of the icy moons of the solar system. We're looking here at the satellites of Jupiter, Saturn, Uranus, and Neptune, and then I've put in Pluto and Charon to represent for themselves and the Kuiper Belt objects. Most of these objects, these moons, have radii of about 1,000 kilometers or so. Ganymede and Callisto and Titan up here are really sort of planet-sized objects in their own right. They have radii of about 2,000 kilometers, and you can see that there's a variety of different types of surfaces on these objects, and let's see, what else do I want to say here? Basically, these objects exist. You can tell, obviously, that we have only limited imaging coverage on some of these objects that have been visited only by one spacecraft. That's certainly the case for Uranus and Neptune. Oh yeah, I also wanted to point out the moons that you guys probably hear about a lot in the news, which include Europa, which is a moon of Jupiter, and there's been a lot of press lately about the moon Enceladus of Saturn, which is actually a very tiny object, and the large moon Titan. Europa, of course, is famous for having a subsurface liquid water ocean. It turns out that Ganymede and Callisto also have oceans. I'll talk about that more in a second. Enceladus actually turns out to be active at present. Currently, we're orbiting Saturn with the Cassini orbiter, and we're getting a lot of information about the moons of Saturn, and we've seen this large plume of water ice coming off of the south pole of Enceladus. And we've also recently dipped below the clouds on Titan to see what the surface looks like. It turns out that Titan, actually the surface of Titan looks like Earth. Titan is the only icy satellite that has a substantial atmosphere, which is composed mostly of nitrogen. Okay, so we can see there are a lot of icy satellites of the giant planets, and they have a variety of different processes happening on them.
Can I ask one question?
Sure.
The principal observational means through which you know there are oceans underneath these icy surfaces is from the magnetic field?
Yeah.
Yeah.
Yeah. Do you want me to talk about that now? I think I may have a slide about it later, but I mean, the basic idea is that this has worked so far only at Jupiter, because Jupiter's magnetic field is actually tilted relative to its spin axis, and so the satellites, the icy satellites, experience an apparent time-varying magnetic field from Jupiter, and this sets up, or they behave as a conductor in the presence of this time-variable field. I'm going to say it wrong if I get any more technical than that. So the idea is that, because these objects, it's actually Europa, Ganymede, and Callisto, they behave as conductors in the presence of Jupiter's field, and so that indicates that there's a global layer of actually salty water underneath. Yeah, that is the best evidence. On Europa, there's secondary evidence just based on the presence of these weird cycloidal cracks on the surface. You can't make, the way that you make those is with the daily tidal stresses. And to get a stress big enough to break the ice shell has to be decoupled from the rocky interior. Yeah. Okay. Did that answer your question?
Yes,
okay.
Thanks.
Okay. So I want to just briefly mention the Kuiper Belt objects. This is a plot of the known Kuiper Belt objects in 2008, although it seems to me to be a little thin. This is a plot of distance in X and Y in astronomical units, and each of these green dots represents a Kuiper Belt object that has been detected. Most of them have been detected through ground-based surveys. You can see the distance scale here is pretty large. The Sun-Earth distance, which is 1 astronomical unit, is about the size of one of the dots. So here's the Sun at the center, Jupiter, Saturn, Uranus, and Neptune, and then the Kuiper Belt. And it's estimated that there's about 30,000 objects in the Kuiper Belt with radii, or diameters, I guess, larger than 100 kilometers. So this is an entirely new class of objects. There's a huge, huge number of them. It turns out, of course, that Pluto and Charon, or Pluto is not really a planet, it's one of a larger class of objects right out at the edge of the solar system. And as we get, now we're starting to get spectra of these objects, and people are starting to look at things like compositional variations and starting to think about what might be going on inside all of these little objects out of the edge of the solar system. Okay. I want to mention also that it's very, very cold out in the outer solar system compared to what you might experience on the Earth. By the time you get out to Jupiter, the effective surface temperature of the satellites is about 130 Kelvin, and liquid nitrogen is 77 Kelvin. Okay, so the surfaces of these objects are really very, very cold, and by the time you get out to the Kuiper Belt, the effective surface temperature of an object out there may be only about 40 Kelvin or so. There's also a general trend just in the solar system, just due to the temperature distribution in the solar nebula, that as you get further away from the sun, there's more ice incorporated in these objects. And as you get further out to Uranus and Neptune, you can have things like hydrocarbon ices mixed in with water ice. Okay, so now we'll talk about the oceans. These are the objects for which we have direct, or in parentheses here, indirect evidence for liquid water ocean. I mentioned one of the ways that we know that there are oceans basically just from looking at the magnetic field. At Saturn, Saturn's magnetic field axis is basically aligned with its spin axis, so we can't do this inductive magnetic field trick at Saturn the way that we could at Jupiter. But there is there's direct evidence now of an ocean on Titan. This is a relatively new result, just looking at the locations of surface features on Titan. It turns out the ice shell appears to be rotating differentially compared to the rocky core of Titan, and there's this indirect evidence for an ocean on Enceladus, just based on the fact that it's so active. The only way to create the amount of heat that's coming out of Enceladus that's been observed by the Cassini spacecraft is with tidal heating. And in order to have a lot of tidal heating, the ice shell has to be decoupled from the rocky interior of the object. I think there's some indirect evidence that that process, that tidal flexing and activity may be going on Triton as well, based on the Voyager images, and I think it's probably pretty likely there's an ocean inside Pluto. Some of the observational people have claimed there's an ocean inside Charon, but I don't really believe it. So anyway, the takeaway message from sort of the last decade of exploration of icy satellites is that most of these objects actually have oceans, and that was not expected ahead of time in most cases. Of course, before we really looked at icy satellites in detail, before we sent spacecraft there, it was hypothesized that they could have oceans, and that's purely based on the phase behavior of water ice. So we're just looking at a simple water ice phase diagram with a temperature going from 50 to 350 K and a pressure, from 0 to 1200 MPa. The minimum melting point of water ice occurs at a depth of around 100 kilometers on most of these icy satellites. And so it was expected that, if you could get the interior of the satellite hot enough, that you could actually have a liquid water ocean and your temperature profile would jump across the liquid phase transition. So this was hypothesized before we sent any spacecraft to the icy satellites. Of course, when we got there, all of our ideas about what the temperatures were inside these objects had to change. So I mentioned before that I had started out in this field working on sort of mantle convection inside icy satellites. When I did my research project, we assumed that the temperature profile inside Ganymede and Callisto kind of followed a line similar to this green line here. So you just, they get warmer as you go inside, but we thought that the temperature would never get anywhere close to the melting point of water ice. And of course, if you know that there's an ocean inside the satellite, you know that the temperature profile has to follow something like this pink curve. So you have to jump across that phase transition and have your ocean and then go back into the high pressure ice polymorphs at depth. Okay, so now I'll focus for the rest of the time on the processes that drive resurfacing in icy satellites, and I want to just briefly mention the types of surface features that we see on these objects, and then describe a little bit about their sort of geophysical setting. Okay, so a lot of the scientific and popular interest about the icy satellites is really due to, in part, their subsurface oceans, but also their somewhat bizarre surfaces. The most interesting objects from sort of the outsider's point of view are obviously Europa, which is the moon of Jupiter, which has this ocean beneath tens of kilometers of ice, and Enceladus at Saturn, which I mentioned before, turns out to be active today. So Europa is a member of a group of satellites known as the Galilean satellite family. These are four relatively large moons that all orbit Jupiter in the same direction, and they're in the same orbital plane. So we think that they formed in sort of a subnebula around Jupiter in the late stages of Jupiter's formation. The best observations that we have of these objects come from the Voyager and Galileo spacecraft. Unfortunately, if you've been following planetary missions, the Galileo spacecraft was launched and it was damaged on launch. So its large antenna that it was going to use to send back data, it was all folded up and it never unfolded. So most of the science data that we tried to get back from Galileo had to be beamed back on an antenna about this big, using about the same power as a coffee maker, maybe less than that. So we didn't get global imaging coverage of these satellites the way that we were hoping from the Galileo mission, which is part of why NASA, potentially in collaboration with ESA, wants very badly to go back to Jupiter to do further exploration of Europa and the other moons. Okay, so there were sort of, in addition to the presence of the oceans, there were two things that we really learned from these two planetary missions about this group of satellites. The first is that there's a gradient in ice concentration in these objects as you move away from Jupiter. So Io, which is the closest to Jupiter, has a lot of tidal dissipation and it's probably blown off most of its ice. So all of that volcanic activity that you hear about on Io is actually silicate material that's erupted onto the surface. It has a very high sulfur content, and that's what's making the colors on the surface. Europa is actually a relatively rocky body. It has a pretty high mean density for an icy satellite. It's about 3 grams per centimeter cubed. So that indicates a largely rock and metal interior, but it has a very thin layer, sort of the outer 10% of Europa is composed of water, obviously some of which is liquid. And the surface temperature, the average surface temperature on Europa is about 110 Kelvin. As you move out away from Jupiter, you come to Ganymede and Callisto, which are these kind of 2 twin satellites. They have roughly the same radius and the same mean density, but they have vastly different interior structures. Ganymede is completely differentiated into a metal core and a rock mantle, and then layers of sort of the high pressure ice polymorphs and ocean, and then an outer layer of ice 1. Callisto, on the other hand, appears to be basically undifferentiated, so it's a homogeneous mixture of ice and rock in the interior. And how you form an object like that and how you keep an object in this state for its entire history is very mysterious, and that's actually one of my current areas of research. So these 3 objects, that Io, Europa, and Ganymede, closest to Jupiter, participate in an orbital interaction where basically every time, Io orbits, let's see, I'm going to mess this up. Every time Ganymede orbits once, Europa orbits twice, and Io goes around 3 or 4 times. Anyway, so they have a tendency to sort of kick up each other's orbital eccentricity, and that's why these objects all experience tidal heating on an ongoing basis. So, and Callisto, I should point out, does not actually participate in this resonance. So as you move away from Jupiter, there's a gradient in the amount of tidal heat that's deposited in each of these satellites. And at Callisto, again, this is 0. So that's probably why, that's probably part of the reason that there's a gradient in ice content as well. Because, Europa may have blown off some of its ice in the manner that Io has. Okay. So the reason why Europa has such an interesting surface is, again, because of this tidal deformation. Basically, what's happening is that Jupiter's gravitational potential stretches and squeezes the ice shell of Europa. Because Europa's ocean mechanically decouples the ice shell from the deeper interior, the ice shell is free to move up and down, and we think it moves up and down about 30 meters during its 85-hour orbit around Jupiter. So what happens is the energy that's stored in Europa's eccentric orbit gets dissipated in its interior. And normally, this process would result in a rapid circularization of the orbit of the satellite. And so, this idea of dumping the orbital energy in the satellite, that would just happen once. Once the satellite is on a circular orbit, you don't have any more tidal effects at all. But these effects persist on Europa and also on Io and Ganymede because that orbital eccentricity is replenished by these dynamical interactions with the other 2 satellites. So this has 2 main effects on the ice shell of Europa. The first is that these tidal forces, we think, can create cracks on the surface of the moon. And the second is that the cyclical deformation is thought to dissipate energy in the warm ice inside Europa.
Can we ask questions here?
Yes.
If this orbit around Jupiter becomes spherical, why does that take away all the tidal effects? We have tidal effects on Earth, and we have it with the moon going circle. It doesn't have to be elliptical.
Right. The reason why the ice shell gets stretched is that the distance between Jupiter and Europa changes if the orbit is eccentric. Yeah. And so you have, let me think how to explain this.
So on Earth, is it a weaker effect? Because we rotate around our axis, so I guess that's
right.
The reason here. So this is a stronger effect before. Right.
Well, it's
okay.
It's hard for me to compare the magnitudes, but you're right. I mean, yeah. it's the same math. I can't think how to explain it right now.
But it's not rotating. I mean, isn't it? It's partly locked, so that the eccentricity is what's giving them, as opposed to, as you said, we're rotating, and so we get this daily.
Right. I mean, what happens is that, if the object is in an eccentric orbit, I mean, this is really exaggerated. The distance between Europa and Jupiter changes, and so the height of the tidal bulge here is much higher than, when it's far away from Jupiter. And so you have this tidal bulge that gets raised and lowered on the object as it goes around in the orbit. If you were in a circular orbit, that would not happen. And you're right, I mean, well, yeah. I'm sorry, I'm very jet lagged. Ask me later in the week, and we'll work all the math out over lunch.
Your own question anyway, so go on.
Okay. No, it's a good question. Okay. So here's just I'm a physicist, okay, so here's my view of Europa's surface geology, which is that there's basically 3 types of features on Europa. There are lines, okay, a lot of lines all over the surface of Europa, and there are lines at many, many scales. There are global lines, and if you zoom in at very high resolution, you find that the entire background geology of Europa is also covered in lines. The second type of feature are impact craters. Here's an example of one, and there are not that many of them. And then there's a third type of feature that I find to be really interesting, which are things that are not lines and are not impact craters. And there are 2 examples. One of them is kind of hard to see here. One is called the Connemara Chaos, and there's another example called Thrace and Thera Macula that you can see on the global view here, and I'll show you some other things that are not lines in a second. These dark patches on Europa's surface are actually radiation processed ice. So we're looking here at the trailing hemisphere of Europa, and the back side of Europa gets hit with high energy ions and particles entrained in Jupiter's magnetic field. They sweep past Europa and smack into the backside and do some interesting chemistry.
Quick question.
Oh, yeah.
So just to follow up on actually both the 2 questions that came before. So the moon is actually phase locked with Jupiter, so it always sees the same phase, or at least the tidal forcing is always in the same direction?
Yeah.
And then do the lines on the largest scale follow the sort of contours of that stretching?
Yes.
Okay.
Yeah. That's been the one scientific triumph of understanding Europa's geology, is that the lines on Europa do actually match up with the expected sort of stress contours. Yeah. Okay. Yeah, so I just want to talk briefly about the surface features that we more or less understand. These lines, we think, are formed by tidal stresses. The daily stresses that get built up in Europa's ice shell are relatively low. They're sort of about tens of kPa. And again, this happens on a time scale of about 85 hours. You can also generate much larger stresses in Europa's ice shell because the ice shell actually rotates differentially from the rocky interior, but it does that on a very long and somewhat poorly understood time scale. So most of the features, the locations and their trajectories of those lines are probably controlled by these daily stresses. Some of the linear features appear to have upwarped flanks. So you have those lines actually consist of 2 parallel ridges where the ridges appear to have sort of bowed up. And we don't have very many examples of topography over these features from the Galileo mission, but where we do have topography, it looks like these ridges are about 100 meters high or so. This double sort of uplift structure is thought to form as a result of cyclical strike-slip motion along these ridges that generates shear heat and thermal buoyancy that causes the ridges to sort of flex upward. This has only been worked out in the last couple of years. Whether this model actually works in detail or not is not really clear to me, but the spirit of it seems to be correct, that you can generate a lot of heat along these global ridges. There are also as I mentioned, a very small number of impact craters on the surface of Europa. These are craters that are formed from very high velocity objects that are in orbit around the sun. So they have impact velocities of 15 to 20 kilometers per second. The fact that there are so few craters on Europa suggests that its surface is young. Estimates of the age of Europa's surface, range from 100 million years to 1 billion years. So it's not very tightly constrained, but we know that it's certainly younger than the age of the solar system. The morphology of the largest craters, such as this one here, which is called the Tyre Impact Basin, suggests that the impactor may have actually punched through the ice shell and reached liquid underneath. So that's actually the best evidence that we have for the thickness of the ice shell in Europa, is from actually looking at the morphology of these craters. Okay, so now I want to talk about the things that are not lines, because I find them to be the most interesting things on Europa. One type of feature is sort of grouped together as sort of pits, spots, and domes. These are relatively small objects, between about 5 to 10 kilometers in size. Here's a field of them impinging on some existing ridges in the background. And remember, I mentioned earlier that the whole surface of Europa is covered in lines. You can see that, there's lines intersecting lines. And then on top of it all, you have superimposed this field of domes. These objects have sort of quasi-regular sizes and spacing around the 10-kilometer mark or so. And so it's thought that these are indicative of thermal or thermochemical convection in the ice shell of Europa, that was part of my PhD thesis research, was evaluating whether that model can work. I should have mentioned at the beginning, the illumination here is from the right. And so some of these objects are standing up and some of them are scooped out and standing low. So you have to kind of turn your head and convince yourself that there's both up and down features on here.
So based on which features imprint over other features, is there some sort of time history towards cracks and domes and pits?
Well, the cracks sit at all stratigraphic levels. The features like this here, which I guess would be, they call it a sort of a complex band, because it's wider. These features may form in a style similar to mid-ocean ridges on Earth. Those things tend to sit somewhat lower in the stratigraphic record. And there is kind of a time progression from the formation of just lines and bands, and at the end of, or I guess the youngest features on Europa tend to be these sort of pits and domes and the chaos regions that I'll show in a second. Unfortunately, because of the limited imaging coverage, we only really have one strip on Europa that can give us enough information to do a sort of relative stratigraphy. But it does appear that there is a change in style resurfacing over time, but it is a little bit subtle. So.
These are really valleys then, or troughs rather than ridges, or sorry, these are ridges rather than valleys. These are going up rather than down. Is that right?
That one,
what you're saying?
This is a down.
But
so this is
the illumination comes from the right. How can it be right on the right hand side?
Oh no, you're right. Okay, this is an upwarped flank. Yeah. I mean, this picture that I showed you here, this is really an idealization. This is one feature, and there are certainly lines on Europa that do not follow this characteristic morphology. So not all of them look like this, but most of them do. So yeah, you're right. This is an upwarped edge on one of them here. The lighting on this picture is a little strange. So this is this type of feature here. This is of the style of double ridge for which that thermal shear heating model has really been applied. This may be, this is a younger feature. It may be less evolved and have undergone less heating. Yeah. Okay. So probably the most interesting regions on Europa are these areas called chaos regions. This is an example, this is a sort of most commonly quoted example, which is called the Connemara chaos on Europa. It's a region about 100 kilometers or so across, and if you look at high-resolution images of the interior, like this little inset here, you can see that this is an area where blocks of existing terrain have sort of broken apart, and they've translated and rotated around, and some of them have even sunk, so they're kind of sticking up like a fin out of the interior, like these little objects here. These chaos regions turn out to be topographic highs. So this whole region actually stands about 100 meters or 200 meters higher than the adjacent ice. There was a lot of work that was done on this during the Galileo mission. There were sort of multiple competing models as to how something like this might form. One idea was that it was a sort of a sea ice analogy, which is that, if the ice shell of Europa is very, very thin, perhaps, and by thin I mean, maybe a few hundred meters or a kilometer, maybe this might represent a place where the ice shell had melted. Unfortunately, that turns out to be a poor analogy for various reasons, and now sort of the prevailing model is that this might represent the top of a giant convective upwelling in Europa's ice shell. There are problems with that model too, though. So not much is really known still about how this type of feature forms. Okay, so I want to briefly discuss Enceladus, which I think is actually scientifically more interesting than Europa. Enceladus is one of Saturn's very small icy satellites. It has a radius of only 250 kilometers, so it's really sort of the size of an asteroid. It has a density of about 1.6, so that indicates it probably has an inner core of about 150 kilometers of rock and an outer ice shell with about 100 kilometers of ice. We're getting a lot of really good information about Enceladus from the Cassini spacecraft. So unlike the Galileo spacecraft that was launched with its antenna completely folded up, they learned the lesson and they fixed the one on Cassini. It's this giant dish, just like the dish from Voyager. So the antenna from Cassini seems to be working, and as a result, we're getting really phenomenal data back about all of the icy moons of Saturn at present. Okay, so Enceladus is very exciting because it turns out to have jets of little water ice crystals erupting from cracks in a warm and tectonically active region at its south pole. So here's just an image of the plume coming off of Enceladus. Each one of these little white streaks is an individual vent source. The sources of these little vents turn out to line up with these linear features that look suspiciously like the double ridges on Europa. We also have estimates of the temperature and the effective thermal emission coming off of this region from the Cassini-Sears instrument, which shows that the stripes themselves are actually warm. So this provides really compelling evidence for that shear heating model that I talked about for Europa's ridges. A similar thing is probably happening on Enceladus. And the great thing about Enceladus is that it's active today, and so we actually can see the moon, we've caught it in the act of resurfacing.
Is it possible to tell much about the composition of the ice that's blown up?
Yes, there are a number of instruments that are looking at the composition. I have a whole bunch of papers I can give you, but I can just tell you right now, most of what they're seeing is water ice. They are seeing some other sort of, small hydrocarbons. I think they're seeing, there's an ambiguity about whether they're seeing nitrogen or carbon monoxide ice. That's still kind of unresolved. And they also have a sort of a dust instrument that can take particles and like vaporize them and then put them into a mass spectrometer, and they've been getting some good results from that. But in general, it looks like it's overwhelmingly dominated by water ice with these minor other constituents. The one thing that we were looking for that we didn't find was ammonia, because ammonia, can lower the melting point of water ice, and that's been invoked as a means of creating, resurfacing on icy satellites. And everybody thought that the satellites at Saturn should have a lot of ammonia in them. We haven't seen any evidence for it at Enceladus or Titan either. So,
but the idea is that you get frictional heating, which then drives the sublimation. Is that?
Yeah. Yeah.
Okay. So. So, and the model for the frictional heating, I mean, you showed it before for Europa, whatever, Nemo's paper. I mean, so it's known in ice streams on Earth that there has to be a lot of frictional heating, and in fact, it determines the dynamics of the system. So, however, here you're at temperatures where you would be considering, at least deeper down, cubic ice. So there's still the issue of the rheology. So it's back to your Dave Stevenson throwing the book on your desk. Is it Glenn's flow law that gives you this, or?
Okay. Well, first of all, I want to say this is Francis Nimmo's model. So I'm not sure I really agree with everything, but I'll tell you Francis's vision of what's going on. The idea is that he splits up the ice shell into an upper brittle portion that has a coefficient of friction, and he's selected a value for the coefficient of friction. And then underneath, he's got a ductile layer that also experiences shear heating. He's not using the Glenn flow law. He's using basically, I think, diffusion creep. In his later stuff, he may be using some grain boundary sliding or something. But yeah, I mean, the amount of heat that you get depends on the coefficient of friction, which obviously is totally unconstrained for these objects, right? And it also depends on the rheology, which is maybe somewhat better constrained. Yeah.
So this was the infrared image, yeah?
Yeah.
And what do you think is the temperature increase?
Well, yeah. It's somewhere. The effective temperature of the effective temperature without the thermal emission at the South Pole is somewhere like around 70 K, and the temperatures that he's seeing along these lines are 180, 200 K. But the spot size of the instrument is huge on this scale. It's this big. So every pixel that he sees with his instrument actually contains hot material and cold material. So as we get closer, we're trying very hard to fly Cassini as close to Enceladus as possible. I think in the last flyby they got like 35 kilometers away from the surface. That's what gave us this picture here. And so, the problem is that the effective temperature increases as the resolution goes down, right? So, if we got 100 meters away, you might actually find out that this was like 260. Right, and I suspect that that's probably the case. Yeah, I don't think thermodynamically you can't have liquid water exposed to bare space, but I suspect that you're getting very, very close to the melting point in the centers of these cracks. Yeah. Okay, so like Enceladus, or like Europa, Enceladus is also deformed by these tidal forces. So we were just talking about these tiger stripes at the South Pole. Are thought to form in a manner very similar to the ridges on Europa. There's, again, that spatial association between the heat and the tiger stripes really supports this sort of shear heating hypothesis. To generate the amount of heat that's observed by the Cassini Cirrus instrument, the sort of up and down and lateral motion of the ice shell has to be very large, probably of order tens of meters, which gives us this indirect evidence that Enceladus, similar to Europa, has a global ocean underneath tens of kilometers of ice. And later this week, I want to talk about possible interactions between this tidal flexing and the behavior of the ice that can help give rise to resurfacing. Okay, I want to say just a few things about Neptune's large moon Triton. So now we're moving away from Saturn, two planets further out to the very edge of the solar system to Neptune. Triton is thought to be a captured Kuiper Belt object. If Triton were captured, it would have initially been in a very highly eccentric orbit. That orbit would have been circularized by tidal dissipation within Triton. So one way of thinking about Triton is that it's like a Kuiper Belt object that got dragged into orbit around Neptune, and it sweated out all of its interesting chemistry onto the surface where we can see it. And that's certainly supported by few images that we have of Triton from the Voyager spacecraft. Triton looks in places somewhat Europa-like. The surface has lines on it, and the shear heating model for ridge formation to does actually appear to work on Triton, so it may explain the origin of the ridges and the upwarped structure of them. Some of Triton's surface is covered by what's called cantaloupe terrain, so the surface just looks literally like the outside of the cantaloupe. The sort of little bumps here are thought to form from sort of thermochemical convection in an ice and hydrocarbon-rich ice shell. Triton also has these sort of black streaks that indicate that there may be active geysers there. It's still, I guess, I thought that was pretty much well understood and agreed upon by everybody, but I guess not. So I think we need to go back and look at Triton again to evaluate whether it's active today. But it's certainly a very interesting object. Okay, I want to just briefly run through some information about the geophysical setting of these bodies, and that'll help set up my talk later in the week. Okay, so what I'm really interested in understanding in part of my research is how icy satellites are actually resurfaced. And so in a sort of general planetary science sense, to understand why any planet experiences volcanism and tectonics, you need to understand how heat is generated inside the object, how that heat is transported, what are the spatial and radial variations in composition inside that object, and how do all of the heat transport and compositional differences, how do they sort of combine to create forces that can deform the cold surface. A lot of the modeling efforts that I've talked about so far, and the ones I'll talk about later in the week, rely on an understanding of how solid ice deforms in response to an applied stress, but this is at what are sort of known as planetary conditions, and the laboratory data for these kinds of conditions are very limited. The deformation rates inside icy satellites are maybe slower than terrestrial glaciers, but they're not, completely out of the realm of possibility. I mean, the strain rates are sort of 10 to the minus 13 per second, and I've done a small amount of reading on terrestrial, ice sheets, and close to the ice divide, maybe you can have very slow deformation rates of order 10 to the minus 12 or 10 to the minus 11 or something. The stresses that are driving the deformation on icy satellites range from about 1 to 100 kPa. These are sort of thermal buoyancy stresses. Some of the tidal stresses may be a little bit higher. Unfortunately, the field data from Earth in general, are restricted to much higher temperatures than you would get on the surface of an icy satellite. So the approach that I've taken in my research is to try to study icy satellite interiors by meshing techniques from basically the terrestrial mantle convection community and my feeble understanding of ice physics to try to take information from the field and information from the lab, bring it together with a sort of a mantle convection type of model to understand the forces that resurface icy satellites. Here's just a summary diagram of these processes that are important for icy satellite sort of interiors and resurfacing. You have heat generated by radiogenic heating in a fully differentiated object. All of the rock has sunk to the center of the satellite, so the ice shell is really heated from beneath. You may also have tidal heating in the rocky part of the object. That's probably the case in Europa. At the surface of this rocky layer, you may have silicate volcanism. There's been a lot of sort of speculation that there might be, hydrothermal vents on the surface of Europa's rocky core that could be affecting its ocean chemistry. Okay, and then you have the ocean that decouples what's going on in the rock from what's going on in the outer ice shell. In this ice shell, you can have shear heating like we talked about, maybe going on in Enceladus and Europa. You can also have tidal dissipation in the warmest ice. If the ice shell is heated from below and it's very cold at its surface, you may be able to drive convection within the ice shell itself. You have probably a lot of cracking of the surface from these daily tides. And finally, I just want to say that there's this idea, and there's been an idea for a long time, that you could actually erupt liquid onto the surface of an icy satellite. At this point, whether that occurs or not is really not very well understood. The driving force for actually erupting a liquid which has a negative buoyancy compared to the sort of ambient ice shell, that driving force is really not very well quantified or well understood. So ever since the Voyager era in the 1980s, people thought that the smooth surfaces of the icy satellites may be due to flooding of the surface with liquid. I don't really think, personally, I don't really think that that happens, but if you read the literature, you'll hear a lot about that.
What type of turnover times for the ice are you thinking of?
It's about 100,000 to 1 million years. Yeah. Okay. I just want to mention the process of solid-state convection in the ice shell, because this is what I do a lot of research on. So here we're just focusing again on only the outer ice shell. These chaos regions and also the pits and spots and domes are thought to form as a result of convection in the ice shell. Usually when people model this, it's just thermally driven convection. And so the sort of Rayleigh number that you're familiar with from terrestrial mantle convection studies has a similar definition for icy satellites. It's just the ratio between the density, the gravity, coefficient of thermal expansion, the temperature difference between the surface of the ice shell and the bottom of the ice shell, the thickness of the ice shell cubed, the thermal diffusivity, and the viscosity. We're looking here at just some sort of sample simulation results of convection in a sort of 100 by 100 by 30 kilometer piece of an ice shell. Here it's just heated from beneath. The viscosity of ice is strongly temperature dependent, like most materials. This here I've just used a simple Newtonian diffusion creep rheology. The Rayleigh number for the ice shell on Europa and Enceladus is pretty low. It's lower than Earth's mantle, so you know, Earth's mantle may be like, I don't know, 10 to the 7 or something like that. For Europa, it's about 10 to the 5 or 10 to the 6. So the convection is somewhat sluggish, and in a basally heated ice shell, you get these very localized upwellings, and if you squint, you could convince yourself that this might form those little domes that you saw on the surface of Europa, but that hasn't really been demonstrated conclusively yet. Okay, so I just want to finish up here by pointing out the general observation, which is that most of the icy satellites that experience this tidal flexing over a very long period of time show signs of resurfacing. And the objects that have not experienced tidal flexing in general do not show signs of resurfacing. All of these bodies that have been tidally flexed have features that basically are linear. Okay, so here's an example of, you know, Europa, which is a relatively small object with a thin ice shell, versus its neighbor satellite Ganymede, which is a very large body. You know, it's about twice the size of Europa, and you know, it experiences tidal flexing, and you also make linear features all over the surface of Ganymede. These global scale lanes of light terrain, if you zoom in on them at very high resolution, they turn out to just these sets of parallel lines. So most of these sort of linear features, the orientation is controlled by these tidal stresses, and in general the formation of those linear things is pretty well understood. But how this sort of cyclical flexing of these satellites leads to the generation of heat in the ice shell, and how the cyclical flexing also leads to resurfacing in general is not very well understood. And that's, I'm hoping to be able to talk to some of the ice physics people here about what may be going on inside these satellites and how the cyclical flexing may affect the ice. I just want to hit one more note about Enceladus here. Enceladus is really sort of the Rosetta Stone. It's the satellite that's going to help us figure out how all of the other satellites work, because we're lucky enough to observe Enceladus during the time that it's being resurfaced. And that, I think, is not true of Europa. I think that all the activity on Europa stopped about 10 or 15 million years ago at least, and that there's really not a lot going on there today. So these estimates of brightness, temperature, and heat flux from the south polar terrain of Enceladus give us an opportunity to argue for or against different types of resurfacing processes. And in my case, I'm very excited because you know, I think that the ice shells of the satellites convect. Not everybody believes that. I think that the fact that there's this large region of very warm ice suggests that there's a giant convective upwelling underneath Enceladus's ice shell. Since we have an estimate of the amount of energy coming out of this region, we can use that estimate to argue for or against different types of convection underneath the outer surface of the ice shell. Okay, so finally, just to summarize the sort of points of this talk, I hope that I've convinced you that the solar system has a lot of icy objects. They potentially have very interesting interiors and surfaces. Most of the objects, at least the large ones, have liquid water oceans underneath a few, maybe tens of kilometers of solid ice that's at a very low temperature. And I think that tidal flexing is a key factor for resurfacing on these objects, and I'll talk about that later in the week. Thanks.
Questions? Excellent.
So what about the relative importance, or any importance at all, of radioactive decay for the heating? Is that completely excluded for all these small objects?
Well, the amount of tidal energy that is created inside these things is probably about a factor of 100 larger than the radiogenic heating.
Yeah.
But if you have a satellite where there are no tidal effects and you only have radiogenic heating, you can probably warm the interior to the point where you can create an ocean. That's obviously been the case for Callisto. But in general, they're going to be much larger. But what I think is that the tidal flexing is not only important from the viewpoint of heat. I think it does something to the ice at the upper surface. And so an object that is heated only from within by radiogenic heating, the surface ice may be too stiff to actually deform in response to these very small thermal buoyancy stresses in the interior. But yeah, the radiogenic heating is the key heat source for most of these things. And if you think about something like a Kuiper Belt object that's sitting alone all by itself way at the outer edge of the solar system, that is the only source of heat.
I have two questions and a comment. First question is that when you first talked about Enceladus, you talked about its total radius, and then a rocky core and an icy shell, and then later you talked about water. So,
Yeah.
How?
The structure is.
Yeah, there's a veneer of an ocean between the core and
Yeah. Well, we don't really know. But given the amount of energy that's coming out of the south polar terrain, we think that Enceladus is completely differentiated. So all of the rock has gone to the center, and all the ice has sweated out close to the surface. And whether there's an ocean or not, again, is not really known. But I mean, just based on the amount of energy that's coming out of that area at the South Pole, you can't make that much energy with radiogenic heating. And so probably what's happening is you're getting tidal dissipation in the ice shell of Enceladus, but it's all concentrated in that South Polar region. And in order to get the kinds of strains and the strain rate necessary to create the amount of tidal energy coming from the South Polar region, the ice shell has to be decoupled from the rock. Yeah.
So that's the first question. Second question is, in your last few slides, you showed the temperature at the underside of the ice being 273, but it could, we have eutectics that could be 70 degrees different.
Right.
And the Rayleigh number is obviously sensitive to that. Is there any sense of what the chemistry of the ocean would be?
Yeah.
Besides that ionic?
Yeah. Let's see. For Europa, there's been a lot of work done on Europa and a little bit less work done on Enceladus. And in both of the cases, the idea is that, you have these sort of water-rock interactions that, could maybe leach out things like magnesium sulfate. The ocean could be very sort of salty, but the salt is really sort of magnesium rich. And how that affects the sort of temperature of the ocean and the temperature of the base of the ice shell and everything. I mean, obviously it does, but unfortunately that's really unconstrained because that liquid, never really makes it up like onto the surface. So there are sort of end member models ranging from people such as myself, like who are physicists and try to make things simple, and so we assume that it's pure water ice, ranging all the way to the, geochemists who come work on Europa, who, in the extreme view, the entire ice shell could be loaded with magnesium sulfate, right? But, there's a limit to how much salt you can put in the ocean, or in the ice shell, because it's got to be gravitationally stable, like, over the ocean. But, yeah, I mean, there really is kind of a wide range of possible chemistries, so.
So then the comment is, at the end you show, Rayleigh number, if you do boost-nest convection, you get a nice hexagonal planform, but then of course we saw all these linear features on Europa, for example, so there has to be something that breaks the symmetry of that.
Yeah.
And even without external forcing, for example, the tidal forcing, if I take a non-boost nest system and ask, in a box, and I turn on a Rayleigh number, then there is also a symmetry breaking, which gives you a non-hexagonal planform to your convection pattern. So,
what's going on?
Yeah, how would
okay.
you go? How would you distinguish one pattern from the next, given?
Okay. Well, let me say that the linear features on Europa probably do not form from the type of convection that I was showing you here. Okay, that, the nice hexagons and everything I was showing you, that's, first of all, that's for a basally heated system, okay, and the ice shell of Europa is probably heated from within. And so then you get a planform that's much more like what you would expect for the Earth. So there are no upwellings, there's just little cold drippings down from the surface. The locations of those, most of the linear features is probably controlled by the tidal cracking. So I showed you that, well, let me see if I'll screw it. There was that feature that I was pointing out to you guys that I called a band, and it was a place where there was a line, but then, it was kind of wider, right? And so it looked like maybe the surface had actually ripped apart. Mm-hmm. The idea is maybe, maybe you have sort of like a top-down thing happening. So you have convection happening, in the ice shell, and you have the tides come along and make a crack, and they create a weak zone that then can be exploited by the thermal buoyancy stresses from convection to kind of pull the surface apart. So those are the kinds of interactions between convection and tides that people are thinking about in terms of how you form resurfacing. But there are obviously a lot of other things that could be going on as well that, beyond my cute toy model.
Is it possible that it's a kind of material coming up from the ocean into the ice shell, so that you get some information about the conditions in the ocean or some material?
Well, that is the hope, that that material that comes up in an upwelling would have entrained parts of the ocean. Unfortunately, there hasn't been any evidence of that yet. And part of what makes it so complicated is that the ice on the surface of Europa is heavily processed by radiation from Jupiter and particles hitting the surface. So everything within the top 1 meter on Europa that could be sensed with a spectrometer, right, from orbit, all of that basically is reflecting the interaction between the stuff in Jupiter's magnetic field hitting the ice on Europa. Mm-hmm. And so even if there was some interesting ocean chemistry that had been dumped onto the surface on Europa, we probably would not be able to see it. On Enceladus, however, there's much more hope that you might be sensing the ocean chemistry, if in those little cracks, because the material that comes out of those cracks, maybe it's coming from a subsurface liquid pocket, maybe it's coming from a global ocean. We don't really know. It could also just be coming from really hot material that's exposed to the surface, and maybe there's no liquid involved. I think the likelihood of finding chemistry indicative of the ocean is much higher on Enceladus than on Europa. But yeah, it would be nice if we had that information, but I don't think we're going to get it.
One from Harold, and then.
Was there any time in the history of those satellites where you could have formed other types of ice, like backlights or something like that?
Yeah, they probably did. They probably did.
Survive up to now?
Yes. trying to think. There's been some work done on that recently for Titan. Titan has this atmosphere that's very nitrogen rich, but it also has methane in its atmosphere, and methane is destroyed very quickly from UV photolysis. So people think that there must be a crustal source of methane. One thing that's been suggested is methane clathrate ice, you know, inside Titan, and it's just outgassing, and there's stuff streaming out from the interior. The stuff that the building blocks of these satellites, you know, are these little ice grains from the solar nebula that get, you know, pulled in, right? And it's possible that you can create clathrate in the solar nebula, and then what happens to that during the little impacts that accrete the satellite, and you know, whether you compress it and heat it up enough to break the clathrate is not very well understood, but it's certainly possible. And people have talked a lot about, you know, what if the whole ice shell, you know, Europa is, you know, made of like methane clathrate? How would that change things? That's also been looked at as a possible source for the plume activity. If you're explosively decompressing clathrate on Enceladus, you know, that could be wafting little ice particles up. So, yeah, for sure.
Well, if it's all methane clathrate, then British Petroleum can go and...
I know, that's an excellent funding source for a new mission.
Right.
That's a good point. I hadn't thought of it.
Excellent.
Do you know anything about the radial or spatial profile of the heating? And is that also taken into account in your box simulation of convection?
We know information about the radial profile.
Mm-hmm.
The spatial profile, no. People will claim that they know the answer to that. I don't think that they do.
So you assume
It's
it's
radially,
symmetric.
yeah, spherically symmetric. And no, that was not included in my model.
Mm-hmm.
I'm hesitant. There are equations that exist in the literature to do spatially varying tidal heat.
Mm-hmm.
I'm not sure that those equations are right, and so until I convince myself that they're correct, I don't want to put them in the model. So what I usually do if I'm trying to approximate tidal heating, I just assume that it's uniformly distributed in both radius, because the ice shell is very, you know, it's thin,
Mm-hmm.
and so I just assume usually that it's, you know, uniformly distributed in both radius and in spatial coordinates. But that's because I'm very conservative about this
Mm-hmm.
type of modeling. There are other people who are more liberal, and they're willing to plug in these funky equations
Mm-hmm.
and get funky answers. I'll show some of those later in the week. So.
Mm-hmm.
Like Francis Nemo. No comment. I just made a comment. But we just, maybe we can stay on schedule a little bit if we could come back at 11:30. But before we break up, I just want to plant the seed. You saw the bottom of this convecting shell of ice in contact with an ocean. So now what we're going to hear about in the next talks are what happens at such an interface, what has to happen, and what may be the constitution of something that grew from an ocean. And then what could possibly live in that space. So let's try to get back together around 11:30 and carry on.